Welcome back to the Deep Dive. It is January 2026. And I have to say, if you've been paying any attention at all lately, you know the world has, well, it's completely shifted. I mean, we're not just talking about chatbots writing bad poetry anymore. We're talking about Nobel Prizes.
It really is the era of AI growing up, isn't it? I mean, when the 2024 Nobel Prizes in both physics and chemistry go to AI breakthroughs, that's the scientific establishment saying, okay, this isn't a fad, this is a fundamental tool now.
But that creates this weird feeling for me, and I think for a lot of people. On one hand, you have Nobel Prizes. On the other, you see all these headlines about job losses, huge energy consumption, and just, general confusion. It's loud out there.
It is.
So our mission today is to cut through all that noise. We've got a stack of some heavy-hitting sources. There's the massive AI Index Report 2025 from Stanford, some pretty sobering papers from MIT about the physical limits we're hitting, and then some actual engineering blueprints.
It's the perfect roadmap, really. We're going to move past the AI is magic hype and look at the reality of 2026. In the short version, AI is breaking every benchmark we have, but it's also hitting some very, very real walls.
Let's start with that view from the top then, the Stanford report. As I said, this thing is a beast, but one stat it stopped me in my tracks. The money.
The investment numbers are eye-watering. The report pins U.S. private investment at, $109.1 billion for 2024?
$109 billion.
And generative AI alone just swallowed about a third of that. But what's maybe more interesting than the total amount is what that money has bought us in terms of efficiency.
This was the comparison that just blew my mind. They looked at the cost to query a model, basically, how much it costs to ask the AI a question.
Right. And they compared the cost of using a model at, say, a GPT 3.5 level of performance, which was state-of-the-art back in late 2022.
For now.
Yeah, to what it costs now. In just under 2 years, the price dropped by a factor of 280.
280 times cheaper. It's hard to even visualize that. That's like the difference between buying a luxury car and buying a sandwich.
And that changes everything. It means startups, students, researchers, they can all run experiments that only tech giants could afford just a few years ago. It democratizes the usage of AI. But, and there's always a but.
There's always a but.
While access is getting democratized, the creation of these top models is going the other way.
You're talking about the industry takeover part of the report.
Yeah, exactly. In 2024, nearly 90% of the notable AI models came from industry, not academia. Universities just can't afford the electric bill anymore.
And speaking of power, the report gets into the whole U.S. versus China dynamic. So U.S. investment was over $100 billion. China's was, around $9 billion?
Just over 9, yeah. 9.3 billion. On paper, it looks like a blowout.
It does.
But the nuance is fascinating. Yes, the U.S. leads in total investment in the sheer quantity of models, but China is aggressively closing the quality gap. On the big performance benchmarks, the difference between the top U.S. model and the top Chinese model has shrunk to, near parity.
So the U.S. is spending 10 times the money for almost the same quality result.
In many areas, yeah. And China is actually leading in the number of AI patents in robotics. It just suggests that throwing money at the problem isn't the only solution.
Okay, so let's talk about what winning even looks like. We used to talk about the Turing test. Can a computer fool a human? That feels so quaint now.
Oh, the Turing test is obsolete. Totally. The report basically says AI crushed the old benchmarks. We're looking at things like SWE Bench now, which tests software engineering.
These aren't just multiple choice questions.
Not at all. These are complex, real-world coding problems.
I have the numbers here. In 2023, AI models solved about 4.4% of those problems. Basically, a failing grade.
Miserably failed the interview.
But 2024, 71.7%. That's not a learning curve, that's a vertical line.
It is. It's a total paradigm shift. But, and this is where we have to pivot, having a model that can do that is very different from understanding how it does it. And I think a lot of us still treat these things like a black box.
I am definitely guilty of that. You throw around deep learning and neural networks at parties, but to really get the rest of this, we kind of have to open that box up.
This is so crucial. To see where AI is going, you have to get where it came from. So you have AI at the top, the big umbrella. Under that, machine learning. And deep learning is just a specific subset of that.
And the big shift, the whole reason for this explosion, is about something called feature engineering.
Correct. In what we call classical machine learning, the humans had to do all the heavy lifting. We have this great paper in our stack about malware detection that shows this perfectly. Researchers were trying to teach a computer to spot a virus.
So in the old way, a human expert had to sit down and literally tell the computer, okay, look for this specific file size or look for this line of code.
Exactly. That is feature engineering. The human defines the features. And in that study, they used a classical method, and here's the kicker. With those human-picked features, it actually outperformed the deep neural networks in some tests.
Wait, really? The old school way beat the new hotness.
In that specific case, yeah, because the human experts gave the model a shortcut. But deep learning's superpower is that it does automatic feature engineering.
Meaning it figures out what to look for all on its own.
Right. Think about how a neural network sees an image. It's a hierarchy. The very first layer of neurons might just look at raw pixels and say, is there a line here? That's it, just a line.
Okay, simple enough.
The next layer up takes those lines and says, oh, do two lines meet here? That looks like a corner. The layer after that sees three corners and goes, hey, that's a triangle. And eventually, way up in the network, a layer says two triangles and a square. That's a cat's face.
So it's building these complex concepts from simple little blocks, layer by layer, and a human never told it what a corner is.
Precisely. It's not magic. It's just really, really clever optimization. It's finding the best mathematical way to represent the data. But, and this is key for what's next, because it figures this out on its own, it requires absolutely massive amounts of data and compute.
So the computer has to do the work of the human expert, but like a billion times over.
Exactly. And that scale introduces chaos.
Which brings us to the engineering reality part. We know these models are smart, but building a reliable product with them is apparently a nightmare. We have this paper from ArcSIF, Design Patterns for AI-Based Systems. It says something like 70 to 80% of AI projects fail.
That is the dirty little secret of the industry. Having a smart model just isn't enough. You need a system around it. The paper argues we're in this sort of Wild West phase of development. Duct tape and prayers. We need blueprints.
I love this part because it felt so practical. One of the patterns they talk about is two-phase predictions.
This is a great one. Think about it. Running a massive model in the cloud is expensive. It's slow. You don't want to use all that power to answer something simple like, what time is it?
So you use a smart intern and a wise professor.
That is a perfect analogy. You put a small, fast, kind of dumber model on the user's phone. That's the intern. It handles all the easy stuff right away.
And if the intern gets stumped?
Then, and only then, it sends the hard question up to the massive professor model in the cloud. It saves money, saves battery, and it's just a better experience.
Another pattern that stood out to me was encapsulating ML models. This seems to get at that black box fear people have. It's basically a guardrail.
This is non-negotiable for safety. AI is probabilistic, right? Ask it the same question twice, you might get slightly different answers. You cannot have that in a self-driving car.
So you wrap it in hard-coded rules.
Exactly. You build a traditional software wrapper around it. If the AI suggests something physically impossible, like telling a car to turn its wheels 90 degrees instantly, the wrapper just says nope and blocks it. It's a reality check.
And then there was the canary model.
Ah, the canary in the coal mine. When you have a new version of your AI, you don't just push the update to all 100 million users at once. That would be insane.
Right.
You deploy it to a tiny fraction first, maybe 1%.
The canaries.
But the canaries. And if the model starts hallucinating or crashing, only a few people are affected. You can roll it back before it becomes a headline. It's just basic risk management.
I want to ground this in a real-world example. We've got this great case study about an automotive factory. I love this story because the AI found a pattern the humans totally missed. But the solution was surprisingly analog.
This is such a classic Sherlock Holmes moment for AI. So this factory was making metal castings, and they had a quality problem. Some parts were warping as they cooled, and the engineers were stumped. They checked everything.
So they just fed all the data they had into a machine learning model?
All of it, from the machines, the sensors, the environmental monitors, everything. They just let the AI hunt for correlations, and it found one. A statistical link between the defects and the HVAC system.
Yeah, the air conditioning.
One specific air vent. It figured out that when the AC kicked on, defects spiked. Turns out, the vent was blowing cold air directly onto the hot metal, cooling it unevenly.
That is incredible. The engineers are looking at the giant robot arm, and the AI is looking at the wall vent.
But here's the crucial part. The AI didn't fix it. It just pointed. The solution wasn't code. The solution was for a person to go and build a physical shield around the cooling area.
Literally just block the vent.
Basically, it's that perfect expert plus AI synergy. The AI finds the hidden pattern, the human provides the context, and the common sense fix.
So we have these design patterns to build systems safely. We know they work, but we have to talk about the cost, not the money, the computational cost. This brings us to that MIT paper, The Computational Limits of Deep Learning. This is where the optimism hits a bit of a speed bump.
This paper is the reality check. We talked about how these models are over-parameterized, tons of neurons. That's how they learn so well. But the MIT researchers point out this method has and I'm quoting here, a voracious appetite for compute.
The math is kind of scary, isn't it? It's not a one-to-one relationship.
Not even close. To get a linear improvement in performance, just to get a little bit better, you need an exponential increase in data and computing power. To cut your error rate in half, you might need 500 times the compute you used before.
500 times the power for twice the performance. That's a terrible deal.
It's the law of diminishing returns on steroids. And we are seeing training computation needs double every few months. The MIT paper just flat out says this is unsustainable.
And the environmental cost is exploding right alongside it. They compared AlexNet from 2012 to Llama 3.1 from 2024.
It's staggering. AlexNet's training emitted about 0.01 tons of CO2, basically nothing. Llama 3.1 estimated around 8,930 tons.
Wow.
That is just an astronomical increase.
So the argument from MIT is basically the party's over. This brute force method has to end.
They argue we're hitting a wall. We can't just keep throwing more chips at the problem to squeeze out another 0.5% of accuracy. We need a fundamental rethink of the algorithms themselves. We have to get smarter, not just bigger.
It really feels like we're at a crossroads. Because on one hand, you have these massive costs and limits. But on the other, the impact on humanity, especially in medicine, is undeniable.
That's the counterweight. In 2015, the FDA approved 6 AI medical devices. In 2023, that number was 223. And these aren't just admin tools. They're helping detect cancer from X-rays, sometimes better than a human doctor.
But again, the report says the best results come from that AI plus doctor collaboration. It's the factory story all over again.
Exactly. It's not about replacement, it's about augmentation. And you can't forget AlphaFold. Solving protein folding is going to change drug discovery forever. That's a tangible benefit that maybe justifies a lot of compute power, but it doesn't solve the long-term problem.
And despite these medical miracles, the Stanford data shows people are still pretty wary. There's this massive public opinion divide.
It's a really interesting geographical split. Optimism is sky high in places like China, Indonesia, Thailand. We're taking upwards of 80% of people think AI will help them. But in the West, the US, Canada, France, skepticism is the dominant mood.
Why the difference?
It seems to boil down to trust. The data shows people in the West just don't trust that their data is safe, and they don't trust the companies to reduce bias or handle this technology responsibly.
Which brings us right back to those design patterns. Things like ethics, credentials, and safety guardrails, they aren't just for developers, they're trust features for the public.
Exactly. The tech is advancing faster than the trust infrastructure. That ethics credentials pattern is about creating a verifiable audit trail, proving the AI was trained on compliant data. It moves us from just trust us to here's the proof.
So let's pull all this together for 2026. We've got cheap, powerful models, we have incredible performance, but we're facing a computational wall and a pretty serious trust deficit.
We are at the end of the brute force era. For the last decade, the strategy was simple. Add more data, add more chips. That worked. But it's hitting diminishing returns. The next 5 years won't be about who has the biggest data center. It'll be about smarter engineering.
It's about shielding the air vent instead of building a bigger factory.
Perfectly put. We need to move from, look what this can do, to how do we make this reliable, efficient, and safe?
That MIT paper left us with a really provocative thought. They suggest that unless we find a way to improve performance without just adding more compute, deep learning progress could just stagnate.
And that is the trillion-dollar question. Are we approaching a plateau where 2027 just looks a lot like 2026? Or is there a new paradigm shift? Something as big as the move to deep learning was waiting just around the corner. History suggests we find a way, but the math says it's going to be very, very hard.
It's a fascinating time to be watching. As you go about your week, maybe look for the patterns in the AI you use. Is it a smart intern handling your basic request, or is it a canary testing out something new on you?
And ask yourself, is it actually solving the problem, or is it just blowing cold air on the casting?
Thanks for diving in with us. We'll see you next time.